In April of 2025, a team of astronomers at the University of Cambridge detected chemical signatures in the atmosphere of a distant planet that, on Earth, are produced almost exclusively by living organisms. The statistical confidence of that detection was 99.7%. No major press conference was called. No NASA administrator stood at a podium. No front page carried the story. The paper was uploaded to a preprint server on a Wednesday, and the world moved on. What you are about to hear is not speculation. It is not fringe science. It is the peer-reviewed finding of one of the most respected astrophysics teams in the world, using the most powerful space telescope ever constructed, pointed at a planet that sits squarely inside its star's habitable zone, 124 light-years from where you are sitting right now. The planet is called K2-18b. And the question this video is going to answer, the one the scientific community has been arguing about since that April paper dropped, is not whether the signal is real. The signal is real. The question is what made it. That distinction is everything. And by the time this video ends, you will understand exactly why that distinction is the most important unresolved question in science today. There is a second story running underneath the first one. It is the story of what happened after the detection, the counterpapers, the reanalyses, the public disputes between research teams, and what one senior astrophysicist called the most contested scientific debate in exoplanet science in years. That story matters just as much as the detection itself, because in 2025, the way science argues about a finding like this tells us as much about the state of the search for life as the finding does. We begin with the planet. K2-18b was discovered in 2015 by the Kepler Space Telescope during its extended K2 mission. It orbits a red dwarf star, designated K2-18, in the constellation Leo. The star is cold, small and dim. Its surface temperature is 3,457 Kelvin compared to the Sun's 5,778. Its radius is 45% of the Sun's. It is not visible to the naked eye from Earth. The planet itself is not Earth-like in any conventional sense. It has a mass 8.63 times that of Earth and a radius 2.61 times as large. It sits in a classification astronomers call sub-Neptune, larger than Earth, smaller than Neptune, with a bulk density of 2.67 grams per cubic centimetre. For reference, Earth's bulk density is 5.51, though Neptune's is 1.64. K2-18b falls between those two values. It completes one orbit every 33 days. Its distance from K2-18 is calibrated such that it receives approximately the same amount of stellar radiation as Earth receives from the Sun. That orbital position, combined with its physical characteristics, is what placed it at the center of one of the most consequential hypotheses in modern astrophysics. Sub-Neptunes are the most common type of planet known in the galaxy. The Kepler mission found them everywhere it looked, and yet our solar system contains none. Not one. We have no local analogue to study. Every model we build about their interiors, their atmospheres, and their potential for habitability is constructed without a baseline example. We are working, as planetary scientists sometimes say, entirely from inference. And that is an important fact to hold on to, because everything that follows, every detection, every reanalysis, every dispute, takes place in a domain where the models themselves are still being invented. In 2020 and 2021, Professor Nikku Madhusudhan and his colleagues at the Institute of Astronomy at the University of Cambridge published a series of theoretical papers that changed how the field thought about sub-Neptunes like K2-18b. They proposed a new planetary category. They called it a Hycean world. The name comes from the combination of hydrogen and ocean. A Hycean planet, in Madhusudhan's framework, is a world with a deep, global liquid water ocean covered by a hydrogen-rich atmosphere. These are not gas giants. They are not rocky terrestrials. They are something in between, something that, in theory, could maintain liquid water at their surfaces despite the pressure and thermal conditions that most planetary models would describe as hostile. Before this framework, sub-Neptunes with hydrogen envelopes were largely dismissed as habitability candidates. The conventional assumption was that their thick hydrogen atmospheres would trap too much heat, cooking any potential ocean beneath. Madhusudhan's modelling work challenged that assumption. Under the right conditions, the right stellar distance, the right atmospheric composition, the right interior, a Hycean world could maintain surface liquid water. It could, in principle, be habitable. The concept is very new. There is no confirmed example of a Hycean world anywhere in the galaxy. The category is theoretical, built on models, and the environmental context for any potential biosignatures on such a world is still being developed by researchers who are essentially writing the rules as they go. Madhusudhan identified K2-18b as the most promising Hycean candidate known. Its position in the habitable zone, its size, its atmospheric accessibility, and the observational history already accumulated on it made it the logical first target. When JWST became operational, it was one of the first exoplanets placed on the observation queue. The James Webb Space Telescope launched on December 25, 2021. It is the product of a 3-decade collaboration between NASA, the European Space Agency, and the Canadian Space Agency. Its primary mirror is 6.5 meters across, more than 2.5 times the diameter of Hubble's. It operates primarily in the infrared, yet which allows it to detect the chemical fingerprints of atmospheric gases at the distances that were entirely beyond the reach of any previous instrument. The way JWST reads an atmosphere is through a technique called transmission spectroscopy. When a planet passes in front of its host star, a small fraction of the starlight passes through the planet's atmosphere. Different molecules absorb light at different wavelengths. By measuring which wavelengths are dim during that transit, and by how much, astronomers can identify which gases are present and in what concentrations. It is, in essence, chemistry conducted across 124 light-years. On September 11, 2023, Madhusudhan's team published the results of their first JWST campaign on K2-18b. The paper was accepted in the Astrophysical Journal Letters. The findings were also presented at the first year of JWST Science Conference in Baltimore. What they found stopped the field. Using JWST's NIRIS and nano spec instruments, operating in the near-infrared range between 0.8 and 5 microns, the team detected methane and carbon dioxide in K2-18b's atmosphere. This was the first detection of both molecules simultaneously in the atmosphere of an exoplanet inside the habitable zone of its star. That alone was significant. Methane and carbon dioxide coexisting in an atmosphere has implications. On Earth, methane is chemically unstable. It reacts with oxygen and breaks down quickly. For it to persist in an atmosphere over geological time, it must be continuously replenished. On Earth, biology is by far the largest methane source. On K2-18b, no oxygen was detected. The methane had to be coming from somewhere. But the 2023 paper contained a second finding, one that was treated cautiously at the time, flagged as low significance, and folded into a single sentence of the conclusion. The data showed a faint signal, a hint, at wavelengths consistent with a molecule called dimethyl sulfide. The team did not announce a detection. They noted the possibility. They called for follow-up observations, and then they waited for more data. The significance of dimethyl sulfide, DMS, requires a pause here. On Earth, DMS is produced primarily by marine phytoplankton. When these microscopic organisms die, they release DMS into the atmosphere. It is the compound primarily responsible for what we recognize as the smell of the ocean. It plays a role in cloud formation over the open sea, where its atmospheric oxidation products act as condensation nuclei. It cycles continuously through Earth's oceans and atmosphere. On Earth, DMS has very few known abiotic sources, meaning very few ways it can be produced without biological activity. Its detection in an atmosphere, under the right conditions, has been proposed for decades as a potential biosignature, a chemical marker that could indicate the presence of life. It was precisely this property that made the faint 2023 signal worth noting, and precisely this property that made what came next so significant. The follow-up observations began, the data accumulated, and in April 2025, Madhusudhan's team submitted the results of their second independent JWST campaign. This time, they were not using NIRISS or NIRSPEC. But they were using MIRI, the mid-infrared instrument, observing at wavelengths between 6 and 12 microns. A different instrument, a different wavelength range, a different technique. The choice was deliberate. MIRI probes deeper into the infrared, where the spectral signatures of sulfur-containing molecules like DMS and its chemical relative DMDS, dimethyl disulfide, are more pronounced. If the 2023 hint was real, the MIRI data would either confirm it or eliminate it. The paper was uploaded to RxIV on April 16, 2025. The title was precise and technical. What it contained was not. The MIRI spectral data showed features that could not be adequately explained by the standard atmospheric molecules present in their model. When the team tested every plausible compound against the data, of the best fit, the combination of molecules that most accurately reproduced the observed spectrum included DMS or DMDS, or both. The statistical confidence of that fit was 3 sigma. 3 sigma, 99.7%. In statistics, that number means the probability that the signal is a random fluctuation in the noise is 0.3%. In most branches of science, 3 sigma is considered strong evidence. In particle physics, the confirmation threshold is 5 sigma, a standard that reflects the extraordinary precision of that field's instruments. In exoplanet atmospheric science, 3 sigma has historically been treated as a significant publishable result. This was a publishable result. What it was not, and this is the distinction that almost no headline carried, was a detection of life. The 99.7% confidence refers to the statistical reliability of the spectral signal. It says, there is a pattern in this data that is almost certainly real. It does not say that pattern was made by living organisms. Those are 2 entirely separate claims, and conflating them is precisely the kind of error that does damage to public understanding of science. Madhusudhan's team understood this. Their paper was careful, the language was qualified. They described the finding as moderate evidence. They called for additional observations. They noted explicitly that the association with life, while plausible, remained unconfirmed. The gap between what the paper said and what the headline said was almost complete, and NASA, notably, did not issue a press release. That silence was deliberate. Unlike the 2023 detection, which had received a full NASA communications package, the April 2025 paper moved through the system without institutional amplification. The agency's restraint was itself a signal, one that the scientific community read clearly and that almost no journalist reported. There is something important in that gap, something about how science communicates and how it fails to, something about what we choose to amplify and what we choose to leave quiet. And the full story of K218b lives in that gap as much as it lives in the data. But before we get to the response, before we examine what the rest of the scientific community did with this detection and what it revealed about both the strength and the limits of the finding, we need to understand what DMS actually is, and why its presence on a world 124 light-years away matters in a way that almost no other molecule would. Dimethyl sulfide is not an exotic molecule. Its chemical formula is C2H6S, 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom. It is small, it is relatively simple, and in the context of Earth's biosphere, it is everywhere. Marine phytoplankton, the microscopic photosynthetic organisms that form the base of the ocean food chain, produce a precursor compound called DMSP as part of their cellular chemistry. When those organisms die, or when they are grazed upon by zooplankton, that precursor breaks down and releases DMS into the surrounding water. From there, it enters the atmosphere, where it oxidizes and contributes to the formation of aerosol particles that serve as seeds for cloud formation over the open ocean. DMS is, and in this sense, a molecule that connects the life of the ocean to the climate of the planet that ocean sits on. On Earth, DMS concentrations in the atmosphere are measured in parts per trillion to parts per billion. It is present, but barely. The ocean is vast, and the organisms producing DMS are countless, and yet the atmosphere carries only the faintest trace of their output. The estimated abundance of DMS or DMDS in K2-18b's atmosphere, as inferred from the JWST MIRI data, was approximately 10 parts per million. That is not a faint trace. That is a concentration thousands of times higher than anything we observe in Earth's atmosphere. Thousands of times. Professor Madhusudhan acknowledged this directly. He noted that if the association with life is real, then this planet will be teeming with life. His words, at an ocean so biologically productive that its DMS output would dwarf anything Earth has ever generated. A world saturated with living chemistry. That image is extraordinary. It is also precisely where the scientific scrutiny begins. Because a concentration that high is not just unusual, it is, in the view of several researchers, difficult to sustain even biologically, and it raised an immediate question that would become one of the central problems in the months that followed. If DMS is present at 10 parts per million, where is the ethane? Ethane, C2H6, is a byproduct. In a hydrogen-rich atmosphere, DMS produced at biological scales would react with the surrounding chemistry and generate ethane as a downstream product. The models predict it. The chemistry is well established. If DMS is really there, at the concentrations the MIRI data suggests, ethane should also be detectable. The JWST data showed no ethane. Dr. Eddie Schwieterman at the University of California examined this problem and stated it plainly. The absence of ethane makes me think we have missed something. Not that the signal is fake, not that the planet is uninhabitable, but that the picture is incomplete in a way that demands explanation. Something in the model is wrong, or something in the atmosphere of K2-18b is behaving in a way that does not match what the chemistry predicts. That discrepancy, DMS without ethane, was not the only complication embedded in the April 2025 data. There was a second problem, more fundamental than the first, and it goes to the heart of what JWST can and cannot tell us. Co-author Michael Zhang of the University of Chicago described it with a precision that cuts through the headlines. He said, anything with a carbon bonded to 3 hydrogens will show up at this wavelength. Dimethyl sulfide does, but so do many other molecules. Even with better data, it will be hard to identify DMS uniquely. Read that again. Even with better data. MIRI's mid-infrared observations are sensitive to a class of molecular vibrations, specifically the stretching and bending of the bonds between carbon and hydrogen atoms that are shared by a very large number of compounds. DMS produces a spectral feature in this range. So does dimethyl disulfide. So does diethyl sulfide. So do dozens of other organic molecules, some biological, some entirely abiotic. The feature that MIRI detected is real. What produced it is another matter entirely. This is the spectral ambiguity problem. It is not a weakness in JWST. It is a fundamental constraint of the technique at these wavelengths. And it means that no amount of additional MIRI data alone can definitively identify DMS as the source of the signal. To isolate DMS uniquely, but you would need observations at other wavelengths, or laboratory measurements of candidate molecules under conditions that match K2-18b's atmosphere, that have not yet been obtained. The April 2025 paper was aware of this. It stated the finding as moderate evidence. It named DMS and DMDS as the best fit molecules within the molecular library used for the analysis. It called for further observations. What it did not say, and this is critical, is that no other molecule could explain the signal. It said that among the molecules tested in their model, DMS and DMDS provided the best fit. That is a statement about the model's library, not about the universe's inventory of possible molecules. And that distinction, quiet as it is, became the fault line along which the entire subsequent scientific debate ran. The independent responses began almost immediately. Jake Taylor at the University of Oxford was among the first. His approach was methodologically straightforward. Rather than building an elaborate atmospheric model, he applied what is sometimes called a flatline test, a standard statistical procedure that asks whether the MIRI spectral data is meaningfully better explained by any molecular model than by a featureless flat baseline. The answer he found was, not significantly. Under Taylor's analysis, the MIRI data did not pass the threshold for claiming a statistically robust detection of any specific molecule. The features were present, but the noise in the data was sufficient that a flat line, meaning no molecular detection at all, remained a viable explanation within standard confidence intervals. Madhusudhan publicly disputed this. He characterized Taylor's method as too simple for the complexity of the data involved. Taylor defended his methodology as standard practice in exoplanet atmospheric science. The exchange was professional but pointed, and it established the parameters of a debate that would widen considerably in the weeks that followed. In May 2025, a team led by Lewis Wellbanks at Arizona State University published an analysis that reframed the problem in a way that was difficult to dismiss. Madhusudhan's April paper had tested the MIRI data against a library of 20 molecules. 20 was not an arbitrary number. It represented the compounds most commonly expected in a hydrogen-rich atmosphere based on current models. The best fit among those 20 was DMS and DMDS. Wellbanks expanded the library, not to 30 molecules, not to 50, to 90. When the MIRI data was tested against 90 possible atmospheric compounds, more than 50 of them produced spectral features comparable to DMS and DMDS. More than 50 molecules, the majority of which have no known biological source whatsoever, could have produced the pattern that Madhusudhan's team identified as a potential biosignature. Wellbanks stated his conclusion without softening it. The statistical significance claimed in earlier work was the product of arbitrary modelling decisions that are not acknowledged. That is a serious charge, carefully worded. It is not an accusation of misconduct. It is a statement about methodology, that the choice of which molecules to include in a model is not neutral, and that the confidence level a model produces is only as meaningful as the completeness of the library it draws from. Now, I constrain the library, and the best fit molecule appears more significant than it may actually be. This critique has implications that extend well beyond K218b. Every atmospheric retrieval in exoplanet science involves choices about which molecules to model. Those choices are made based on theoretical expectations, on what we think should be there, given what we know about planetary chemistry. But K218b is not a planet type we have a baseline for. There is no local Hycean world to calibrate against. The models are, by necessity, incomplete, and incomplete models produce overconfident conclusions. Now stay with this, because what Madhusudhan's team did next is, in its way, even more revealing than the original detection. In May 2025, approximately 1 month after the April paper, they released a second follow-up analysis. This time, they searched 650 molecules, 650, and DMS was still among the top candidates, so were diethyl sulfide and methyl acrylonitrile. Madhusudhan himself acknowledged that diethyl sulfide and methyl acrylonitrile are likely not realistic molecules for a planet like K218b. He included this caveat in the paper. He continued to identify DMS as the most plausible candidate. But Wellbanks noted something about that second paper that cuts to the center of this entire scientific argument. He observed, in the span of a month, with no new data, with no new models, with no new laboratory measurements, their entire analysis changed. The conclusion had been updated, the molecular library had been expanded 30-fold, and the statistical framing had shifted, all without a single new photon of data from the planet. Now, what changed was not the observation. What changed was the interpretation. And in science, when the interpretation of the same data shifts substantially in response to criticism, rather than in response to new evidence, that shift itself becomes data about the robustness of the original claim. This is not an indictment of Madhusudhan or his team. They are among the most accomplished atmospheric characterization researchers in the field. What this exchange illustrates is something more fundamental, the system of science working exactly as it is supposed to. A finding is published, it is tested, it is challenged. The original team responds. The community evaluates both positions. The truth emerges, slowly, imperfectly, but eventually, from that friction. The problem is the timeline. The friction takes months. The headlines were instantaneous, and in the space between the initial 99.7% figure and the peer review process that interrogated it, a substantial portion of the public, including many serious, informed space enthusiasts, formed a conclusion that the data did not yet support. That gap is not incidental. It is structural, and it is one of the most consequential features of how modern science communicates with the world. Before we go deeper into the reanalysis battle, and there is more to go, because what NASA's Jet Propulsion Laboratory found when they brought 3 independent teams to the same dataset fundamentally shifts the picture, there is one finding from a completely separate domain of research that deserves to be placed on the table now, because it changes the meaning of everything that follows. In April of 2024, as scientists announced the detection of dimethyl sulfide on Comet 67P/Churyumov-Gerasimenko, a comet, a cold, airless, lifeless rock and ice moving through interplanetary space, and on it, DMS. Then, in 2025, DMS was detected in the interstellar medium, in the sparse molecular clouds that drift between star systems, where no planet exists, where no ocean has ever formed, where no phytoplankton has ever lived. The molecule that was once considered a near-exclusive marker of biological activity has now been found on a comet and in interstellar space, abiotically, without life. This does not mean the signal on K218b is abiotic. It means that DMS can no longer be described accurately as having very few known non-biological sources. It has abiotic sources. They exist. And in 2024, the laboratory experiments demonstrated that DMS can form under simulated exoplanetary conditions, hydrogen-rich atmospheres, photochemical processes, no biology required. The biosignature that anchors this entire story was, in the same period that the story broke, having its foundational premise quietly dismantled by findings in completely different areas of research. Almost no one reported this. There is a version of this story that the science media almost universally told. It went like this. James Webb detected a molecule associated with life on a distant planet. The confidence was 99.7%. This could be the moment we have been waiting for. That version is not false. Every sentence in it has a basis in the record, but it is constructed from a selective reading of the evidence, one that takes the strongest elements of a genuinely complicated picture and presents them as though the complications do not exist. The version of this story that the science media did not tell is harder to summarize. It requires holding multiple things in tension simultaneously. It requires accepting that a detection can be statistically real and scientifically ambiguous at the same time, that a molecule can be a plausible biosignature and an established abiotic product at the same time, that a team of world-class researchers can be both right about what they found and uncertain about what it means. These are not contradictions. They are the normal operating conditions of science at the frontier. K2-18b sits at the frontier, and at the frontier, while what you think you know and what you actually know are separated by a distance that looks small on the page and is vast in practice. Let us now go to NASA's Jet Propulsion Laboratory. On July the 16th, 2025, Dr. Renyu Hu uploaded a paper to AR-Arxiv. The methodology behind it was distinctive. Rather than conducting a single independent reanalysis, Hu organized a collaborative effort across 3 entirely separate research teams. Each team received the same JWST observational data. Each team performed their own atmospheric retrieval independently, using their own models, their own assumptions, and their own statistical frameworks. Then the results were compared. This approach, sometimes called a multi-team blind analysis, is designed to distinguish genuine signal from the artifacts of any single team's modeling choices. If 3 independent teams working separately reach the same conclusion, that conclusion is far more robust than if one team working with one set of assumptions reaches it alone. All 3 teams agreed on several things. K2-18b has a hydrogen-rich atmosphere. Its methane and carbon dioxide detections, first announced in 2023, are robust. The planet's interior is consistent with a substantial water component. The case for K2-18b as a water-rich world, potentially a Hycean candidate, is not weakened by the new analysis. In fact, the simultaneous presence of methane and carbon dioxide at the observed abundances can only be explained by one of two conditions: either a massive atmosphere with roughly 100 times solar metallicity and a bulk water content of 10 to 25% by volume, or a smaller atmosphere overlaying a liquid water ocean. Both scenarios involve extraordinary amounts of water. On DMS and DMDS, all three teams agreed as well. No conclusive evidence. The signal that Madhusudhan's team had identified at 3 sigma confidence was not reproduced under the multi-team framework. More importantly, whose analysis demonstrated something that recontextualized the entire DMS question. Abiotic photochemical processes in K2-18b's hydrogen-rich atmosphere can produce detectable levels of DMS without any biological contribution. The atmosphere itself, under ultraviolet irradiation from its host star, may be generating DMS chemically. If that is correct, and the modeling supports it, then DMS on K2-18b would be an expected atmospheric product regardless of whether life exists. It would be a dead end as a biosignature. Not because the molecule is absent, but because the environment would produce it anyway. That finding did not make headlines either. 3 weeks after the WHO paper, on August 8, 2025, Kevin Stevenson at the Johns Hopkins University Applied Physics Laboratory submitted a paper that closed the circle on the technical criticism with a precision that left little room for interpretation. Stevenson's team examined the MIRI transit spectrum data in detail. They tested multiple wavelength binning schemes, the way the raw data is grouped and averaged before analysis begins, and found that the results were highly sensitive to which scheme was chosen. With Madhusudhan's preferred binning, a DMS or DMDS detection appeared plausible. With alternative binning schemes that Stevenson's team argued were equally valid, 87.5% of retrievals did not support a DMS or DMDS detection. 87.5%. Stevenson's conclusion was that the MIRI transit spectrum is highly susceptible to unresolved instrumental systematics, meaning the signal may not be coming from the planet's atmosphere at all. It may be an artifact of how the data is processed. The paper's title was Direct, Precise, and Unambiguous. K2-18b does not meet the standards of evidence for life. And then Stevenson said something else, something that sits outside the technical argument and speaks to a larger concern. He said, "Just like the boy that cried wolf, no one wants a series of false claims to further diminish society's trust in scientists." That sentence carries weight that extends beyond K2-18b. It speaks to a pattern of extraordinary claims in astrobiology that have not survived scrutiny, each one generating enormous public excitement and then quietly retreating. The phosphine on Venus, announced in 2020, was ultimately attributed to a calibration error in the original data. The methane plumes on Mars have been detected by some instruments and not by others, and remain unresolved. Each of these stories follows the same arc: detection, headlines, scrutiny, revision, silence. Stevenson is warning that the K2-18b story risks repeating that arc, and the warning is not coming from someone hostile to the search for life. It is coming from someone deeply invested in it, someone who understands that the credibility of that search depends on the rigor of its claims. By August of 2025, the landscape around K2-18b's DMS detection had shifted substantially from where it stood in April. The original 3 sigma signal had been challenged by at least 5 independent teams using different methods, different molecular libraries, and different statistical frameworks. The multi-team JPL analysis found no conclusive evidence. The Johns Hopkins analysis found that most binning schemes did not support the detection. The Oxford flatline test found no significant improvement over a featureless spectrum. The Arizona State expansion to 90 molecules found that more than 50 abiotic compounds could produce the same spectral features. Madhusudhan's team did not withdraw their paper. They published a response. They maintained that their analysis was sound within its stated framework. They noted that the disagreements between teams reflected genuine uncertainty about the best methods for analyzing MIRI data, an uncertainty that was not unique to K2-18b but was a challenge across the field. They called again for more observations. They said, with a clarity worth acknowledging, that they had never claimed a strong detection. They had claimed moderate evidence, and moderate evidence, they argued, remained exactly what they had. This is where the story becomes genuinely difficult to adjudicate, because Madhusudhan is correct that his paper was careful. The language of the April 2025 publication is qualified, measured, and scientifically defensible. The problem is not what the paper said. The problem is the gap between what the paper said and what the world heard. And in that gap, and a question that deserves to be treated with the full weight of scientific uncertainty got flattened into a headline percentage. Here is what the scientific record actually supports, as of early 2026. K2-18b is a real planet in the habitable zone of its star. It has a hydrogen-rich atmosphere. Methane and carbon dioxide are robustly confirmed. Its interior is consistent with large quantities of water. The Hycean world hypothesis, while unconfirmed, is not ruled out. The planet is one of the most scientifically significant atmospheric targets known. The DMS and DMDS signal from the April 2025 MIRI data is statistically real at 3 sigma within Madhusudhan's analytical framework. It is not reproduced at the same confidence level under alternative frameworks and expanded molecular libraries. And the molecule that produces the signal cannot be uniquely identified from MIRI data alone due to fundamental spectral ambiguity at those wavelengths. DMS has been found abiotically in the interstellar medium and on comets. Abiotic DMS formation under K2-18b's atmospheric conditions has been demonstrated in laboratory simulations. The interpretation of the signal as a potential biosignature is not excluded by the evidence. Neither is the interpretation that it is abiotic chemistry. The data does not yet distinguish between those two possibilities. More observations are needed, and more observations are being made. Now pay close attention, because the next chapter of this story is still being written in real time, and what is coming from JWST in the months ahead will either narrow this question significantly or expand it in ways no one has yet anticipated. At the end of 2025, a new set of infrared observations of K2-18b's atmosphere was conducted by the team at NASA's Jet Propulsion Laboratory. The data is still being processed. Dr. Renyu Hu, who led the observation campaign, has stated only this: it will include substantially more data than previously published. That sentence is, in its quiet way, one of the most consequential things said about this planet in the past year. More data than previously published. Not a marginal increment, a substantial addition to the observational record. The analysis of that data, when it is released, will be the most comprehensive spectral characterization of K2-18b ever assembled. Meanwhile, Madhusudhan and his Cambridge colleagues have submitted a new manuscript expanding the molecular search to 650 types of molecules for peer review. That review is ongoing. 2 parallel processes, 2 datasets moving toward publication, and between them, a planet that has already changed the way the field thinks about what is possible, regardless of what those analyses ultimately find. Before we reach the conclusion of this story, and there is a conclusion, though not the kind that closes doors, there is a piece of history embedded in the K2-18b record that almost no coverage has mentioned. It is a precedent. And precedents matter in science because they tell us something about the reliability of our instruments, our models, and our interpretations when applied to this specific planet. When the Hubble Space Telescope observed K2-18b years before JWST, researchers analyzing the data found what they believed to be water vapor in its atmosphere. The signal was present, the analysis was published. Water vapor on K2-18b in the habitable zone of its star was reported as a significant finding. It was methane. The spectral features that Hubble's instruments captured and that the models of the time interpreted as water vapor were later re-identified as methane, once JWST's far superior resolution made the distinction possible. The earlier conclusion was not fraud, and it was not carelessness. It was the result of competent researchers applying the best available tools and models to ambiguous data, and getting the wrong answer. This matters for the DMS question in a way that is direct and uncomfortable. We have now been wrong about the atmospheric composition of K2-18b at least once, using an instrument that was the most powerful of its generation. JWST is vastly more capable than Hubble. But JWST is not omniscient. Its MIRI instrument operates in a wavelength range where, as Michael Zhang noted, Spectral ambiguity is a fundamental constraint. The lesson of the Hubble misidentification is not that JWST will be wrong. It is that on this planet, with this atmosphere, in this domain of science, we should hold our conclusions with the appropriate calibration, which is to say, with more uncertainty than the headlines suggest, and with more seriousness than the skeptics sometimes allow. The truth is probably somewhere between the extremes that define the public conversation. Now, it is probably not the case that K218b's atmosphere is teeming with life-producing DMS at concentrations 1,000 times higher than anything on Earth. It is also probably not the case that the MIRI signal is pure noise. What it is, most likely, is real atmospheric chemistry that current models and current observational data cannot yet resolve with sufficient precision to determine its origin. That is an unsatisfying answer. It is also the correct one. Now step back from K2-18b for a moment. Step back from the DMS question and the reanalyses and the competing papers. Step back far enough to see the shape of what this planet represents at a larger scale, because that shape is genuinely extraordinary, independent of whether life is ultimately found there. K2-18b orbits a red dwarf star. Red dwarfs are the most common type of star in the galaxy. Estimates suggest they make up somewhere between 70 and 75% of all stars. The Milky Way contains somewhere between 100 and 400 billion stars. If 3/4 of them are red dwarfs, and if a meaningful fraction of red dwarfs host sub-Neptunes in their habitable zones, then the class of worlds that K2-18b represents is not exotic. It is not rare. It is, statistically, probably the most common type of potentially habitable world in the galaxy. And we had no atmospheric data on any of them before JWST. The 2023 detection, methane and carbon dioxide simultaneously, in a habitable zone sub-Neptune, was the first of its kind in history, not the first hint, not the first theoretical prediction, the first actual measurement. At the first time humanity pointed an instrument at a planet of this type and read its chemistry, the fact that the reading is ambiguous, that the models are incomplete, that the debate is unresolved, none of that diminishes what the observation represents. It is a first, and in the history of science, firsts are almost never clean. There is also the matter of what the confirmed findings, methane and carbon dioxide together, actually imply, independent of DMS. This is a point that was largely buried beneath the biosignature headlines, and it deserves to be stated clearly. Methane and carbon dioxide coexisting in an atmosphere is chemically significant. Methane reacts. In an oxidizing environment, it breaks down. Its persistence in an atmosphere over geological time requires a continuous source. On Earth, the primary source is biology. On K2-18b, in a hydrogen-rich low-oxygen environment, abiotic sources are plausible. Volcanic outgassing, photochemistry, geological processes could all contribute. But the combination of both gases at the observed abundances, as the multi-team JPL analysis confirmed, points strongly to one of two scenarios: a massive, metal-rich atmosphere with a huge water fraction, or a smaller atmosphere sitting on top of a liquid water ocean. A liquid water ocean, on a planet 124 light-years away, inside the habitable zone of its star. With atmospheric chemistry that, while not confirmed as biological, is not inconsistent with biology either. That is the flaw of this story, the absolute minimum of what the evidence supports. And that flaw, before a single DMS molecule is invoked, is already one of the most significant statements about exoplanetary science in the history of the field. Professor Madhusudhan made a statement in the middle of the controversy that deserves to be heard in full, because it frames the moment with an accuracy that the combative tone of the broader debate sometimes obscured. He said, "We have never reached that level of evidence in any of our studies. We have only found evidence at or below 3 sigma. We refer to this as moderate evidence or hints, but not a strong detection." And then he said this: "We are really fortunate to even be at a position where we are having these conversations. We have entered a new era in the search for life beyond Earth where it is possible to detect and debate about potential biosignatures. And this is unprecedented." He is right, both things. The evidence is moderate, and the conversation is unprecedented. Both are true simultaneously, and holding them together, resisting the temptation to flatten one in favor of the other, is what honest engagement with this moment requires. There is a confirmation threshold that physicists use for genuine discoveries. It is 5 sigma. 99.99999% confidence. The detection of the Higgs boson was held to that standard. The gravitational wave detection by LIGO was held to that standard. These are the landmarks of modern physics, findings that changed our understanding of the universe, confirmed to a level of certainty so high that the probability of error was essentially zero. The K2-18 BDMS signal is at 3 sigma. The gap between 3 sigma and 5 sigma is not small, and it is the difference between a result that is probably real and a result that is definitively real. Madhusudhan's team estimated that approximately 16 to 24 more hours of JWST observation time would be needed to reach the 5 sigma threshold, if the signal holds at higher data quality. That is a precise and actionable statement. It means the question is not unanswerable. It means there is a path from where we are to where we need to be. And that path runs directly through the data that Renyuhu's team at JPL is currently processing from their end of 2025 observation campaign. Here is what is at stake in that data. If the new observations confirm the DMS or DMDS signal at a higher significance, if they push the confidence above 4 sigma, approaching 5, the scientific community will be compelled to treat this as a priority finding. And the debate will shift from whether to take the signal seriously to what could have produced it. That shift, if it happens, will be one of the most consequential moments in the history of the search for life. If the new observations do not confirm the signal, if the additional data washes it out, as happened with the phosphine on Venus, the K2-18b biosignature question will enter a period of suspension. The planet will remain scientifically important, the methane and carbon dioxide detections will remain intact, and the search will move forward with other targets. That outcome would be a correction, not a defeat. It would mean the process worked. And if the new observations neither confirm nor rule out the signal, if they produce a more complex picture that requires still more analysis and still more observations, then we will be exactly where science so often finds itself, at the edge of something genuinely new. In the difficult, uncomfortable, necessary space between what we have detected and what we understand. We began with a number, 99.7%. That number travelled around the world in April of 2025. It was attached to headlines that most people read in under 30 seconds, shared without context, and filed away as either confirmation of something they had long suspected or dismissed as hype they had seen before. Very few people sat with what it actually meant. Very few people followed it past the headline into the methodology, the debate, the counterpapers, the abiotic Comet data, the instrumental systematics analysis, the 3-team JPL replication attempt, and the end of 2025 observation campaign that has still not released its findings. You have now done that. And what you have arrived at is not a simpler picture. It is a more accurate one. The number, 99.7%, is real. It describes a genuine statistical pattern in genuine observational data collected by the most sophisticated astronomical instrument ever built, pointed at a planet that sits in the habitable zone of its star, 124 light-years away. That much is not in dispute by anyone. What is in dispute is the source of that pattern. And that dispute, live unresolved, and moving toward a resolution that will arrive in the form of processed data from a JPL observation campaign conducted at the end of 2025, is not a story about scientific failure. It is a story about science functioning at the absolute limit of what current technology can perceive. Consider the geometry of what JWST is actually doing when it observes K2-18b. The planet orbits its star at a distance that places the transit geometry in a narrow window. Each transit is a brief dimming of a faint red dwarf, detectable only because the star is close enough and the telescope sensitive enough to register the difference. During that transit, a fraction of the starlight passes through a planetary atmosphere that is, at most, a thin shell around a world the size of which we have no local analogue. And the chemical information encoded in that starlight, the fingerprints of molecules present in parts per million, is what JWST is extracting from 124 light-years, with an instrument cooled to within a few degrees of absolute zero, operating in a precise thermal balance that must be maintained continuously, analyzing wavelengths of light that span from near-infrared to mid-infrared across an atmosphere whose structure, pressure profile, and chemical inventory are all inferred rather than directly observed. And we are arguing, at this level of precision, about whether a specific sulfur-containing organic compound is present or absent in quantities measured in parts per million. That is not a story about hype. That is a story about the extraordinary reach of human inquiry, of the fact that we can have this argument at all, that we can point at a planet orbiting a star that our naked eyes cannot see and debate the parts per million concentration of a molecule associated with ocean life. That fact alone is one of the most remarkable things our species has ever achieved. But remarkable capability does not produce certain knowledge. It produces better questions. And the question that K2-18b has placed in front of the scientific community is one that will not be answered by a single paper, a single instrument, or a single observation campaign. It will be answered, if it is answered at all, by the accumulation of evidence across years, instruments, and methods, converging slowly on a picture that current data can only sketch in outline. There is something specific in this story that space science communicators, science journalists, and the broader public have not fully reckoned with. It is the question of what we do with moderate evidence when moderate evidence is all we have. In medicine, moderate evidence guides clinical practice in the absence of definitive trials. In law, moderate evidence shapes investigation in the absence of proof. In both domains, there is a framework, imperfect, contested, evolving, for how to act responsibly under uncertainty. In astrobiology, that framework is still being built. The K2-18b episode is, in part, a stress test of an emerging norm. How should the scientific community communicate a 3 sigma signal for a potential biosignature on an exoplanet? What language should researchers use? What language should institutions use? What obligations do journalists have to accuracy when the precise meaning of a statistical confidence level is essential context? None of these questions have clean answers, but all of them are now on the table in a way they were not before April 2025. And that is one of K2-18b's contributions to science that will persist regardless of what the new data finds. Madhusudhan himself placed the moment in its proper frame. He noted that we have entered a new era in the search for life beyond Earth, where it is possible to detect and debate potential biosignatures. Those words carry more weight than they might initially appear to. For most of human history, the search for life beyond Earth was theoretical, philosophical speculation, science fiction, the domain of thought experiments and Fermi paradoxes. For the past few decades, and it has been instrumental, the search for habitable conditions, for liquid water, for the right kind of star, the right kind of orbit. But the detection and debate of actual potential biosignatures on actual worlds using actual spectroscopic data, that is something different. That is a threshold that, once crossed, does not uncross. We are on the other side of that threshold. That is not a small thing. K2-18b is 124 light-years away. A radio signal traveling at the speed of light would take 124 years to reach it. A reply would take another 124. Any civilization that received our signal and replied immediately, we could not hear the answer until the year 2248 at the earliest. The distance is not a number. It is a statement about the nature of our isolation, and about the scale at which the universe operates relative to the timescales of human attention. And yet, across that distance, in a photon of starlight collected over hours of telescope time, we found something. Something that is either a molecule produced by living organisms at concentrations that would dwarf the productivity of Earth's entire ocean, or a molecule produced by chemistry in a hydrogen-rich atmosphere doing what hydrogen-rich atmospheres do under ultraviolet radiation, or a spectral artifact of instrumental systematics that does not represent any atmospheric feature at all. We do not know which. Not yet. But the question is real. The planet is real. The telescope is pointed and waiting, and the data, more data than previously published, is being processed right now in a laboratory on Earth, and by a team of researchers who will, at some point in the months ahead, submit a paper to a journal and that paper will move through peer review, and the community will read it, and the debate will continue. That is how this works. That is how it has always worked. Not in headlines, not in press releases, not in percentage figures stripped of their context and sent into the world to mean whatever the reader needs them to mean. In data and analysis and peer review and reanalysis and correction and accumulation. Slowly, carefully, without certainty until certainty is earned. The universe is not going to tell us its secrets quickly. It has had 13.8 billion years to distribute them across distances that dwarf our ability to cover them. The fact that we have, in the span of a few decades of space-based astronomy, had found a world 124 light-years away that has liquid water and organic chemistry and a detectable atmosphere, that is astonishing. The fact that we are now arguing in peer-reviewed literature about whether the atmospheric chemistry of that world includes a molecule made by ocean microbes, that is almost incomprehensible. We are, by any measure, in an extraordinary moment. Whether K218b turns out to harbour life, or to harbour only the abiotic chemistry of a hydrogen-rich ocean world, it has already done something irreversible. It has demonstrated that the detection of potential biosignatures on an exoplanet is not a future capability, it is a present one. The debate we are having is not about whether such a detection is possible, it is about whether this particular detection is real. That is a different conversation than the one we were having 5 years ago. It is a narrower, harder, more demanding conversation. It is the conversation that precedes an answer. The new data will come, it will be analysed, the picture will sharpen, and when it does, whether it resolves toward biology or toward a biotic chemistry or toward something more ambiguous than either, the significance of K218b will not diminish, because this planet has already shown us something we needed to see, that when we look carefully enough at the right world, with the right instrument, the universe begins to answer back. We just have to be rigorous enough and patient enough to hear what it is actually saying.